Good day, ladies and gentlemen. You are welcome to our lecture number 4 on measurement and instrumentations. Today we are going to look at the analog instruments. From our first lecture, we divided measurement instrument into analog and digital, depending on how they record and display the reading. So today we are going to look at the principle of operation of analog instruments. If you can remember, the analog instruments, they are the ones that give result in a continuous form. That is, they don't have a discrete value. For instance, if you are measuring from 0 to 1, you can have 0.01, 0.021, 0.35 and things like that. But for digital, it will be giving you whole numbers of what you are measuring. So these analog instruments, they are classified also into different classes depending on the principle of their operation. And these principles may depend on magnetic, that is the magnetic effect that takes the reading and display it in analog form. It can be heating effect, and it can be electrostatic effect, and of course it can be electromagnetic effect. So we are going to be looking at this effect one after the other until we categorize them into different classes. Now, the majority of the analog instruments, out of 4 things we have just mentioned, they operate on magnetic effect. If you can remember, magnet and electricity, they are like twin brothers. You can use electricity to magnetize something, and of course you can use magnet to produce electricity. So the effect of heat also is used in instruments like thermocouple, and of course the electrostatic effect is used in what we call electrostatic voltmeters for measuring voltage, and the electromagnetic induction effect is used in induction wattmeter, and of course induction energy meter. Now let us look at the operating torque of any analog instrument. The analog instrument depends on movement of a pointer on scale so that it can show you the magnitude of the unknown you are measuring. So it is operating with torques. We have 3 different torques that are used for analog instrument for movement of the pointer. The first one, we call it a deflection torque or deflecting torque, and the second one is controlling torque, and the third one we call it damping torque. Now let us look at these 3 torques one after the other. Let's start with the deflecting torque. This deflecting torque is the torque which is required to move the pointer of the analog instrument from the 0 point to the point corresponding to the magnitude of the signal we are measuring. Any deflection instrument, it has a total effect of what? Deflecting torque, or the force, or the control torque, or the force, and of course there is what we call damping torque. So this deflecting torque, as I said, it is the part of the torques which is responsible for displacing the pointer from the 0 point to a particular point depending on the magnitude of the signal that we are measuring at that point. So the deflecting torque's value depends on the electrical signal we are trying to measure. And of course, this torque, the deflecting torque, it is the one that helps in rotating the instrument movement, that is from the 0 position to a particular point depending on the magnitude of the electrical signal we are measuring with that analog instrument. And of course, the system that is responsible for producing this deflecting torque, we call it the deflecting system. And I have said this system captures the signal using a sensor, and the magnitude of that is the one that will create deflecting torque in such a way that the instrument or the pointer can move from 0 point to a particular point. The second one is the controlling torque, and this controlling torque is opposite to the deflecting torque, because I told you the deflecting torque is responsible for moving the pointer from 0 point to a particular point. So the controlling torque is acting in the opposite to that. That is, whenever the deflecting torque and the controlling torque, they are equal in magnitude, then the movement of the pointer will be at equilibrium position, meaning it will stay at a particular point depending on the magnitude of the internal signal or external signal we are measuring. And how do we create this controlling torque? We create it using a spiral springs, or sometimes using the force of gravity, and it is used to produce this deflecting torque. If we can open any analog instrument, you see that the pointer is attached. That's the pin on which the pointer is attached is connected to a spiral spring. Its function is to produce a counter deflection in such a way that whenever it is moving from 0 to a particular point, that's a controlling torque will now place it in equilibrium. Now, the system which is responsible for producing this controlling torque, we call it a controlling system. And as we have said, the torque is what? Controlling torque. So, what are the functions of this controlling torque? The controlling torque has functions. First one is to produce a torque which is equal to the deflecting torque and opposite to the deflecting torque at the final point at which the position of pointer remains, where we are going to take our reading. The second one is to bring the movement of the system back to 0 whenever we remove our signal that we are measuring its magnitude using analog instrument. And the third one, as we have seen, is what we call the damping torque or the damping force. We said we have 3 torques: the deflecting, controlling, and the third one is damping torque. Its function is opposite to the direction of movement of the system. That is, if it is moving from 0 to a particular point, this damping is trying to bring it back, just like the controlling torque is doing. And the function of this deflecting torque is to bring the moving system to rest. That is, to prevent it or protect it from oscillating back and forth like that, so that it will be in a particular point and it will stay there quickly. And the ability to remove that oscillating is what we call the damping, and the torque that is doing that is called the damping torque. And of course, this damping torque can be created using air friction or fluid friction, and sometimes using eddy currents, which can produce this damping torque: the air, the fluid, and the eddy currents. Anybody who passes through secondary school physics, electricity, you're supposed to have read about what is a eddy current. Now, whenever the deflecting torque is found to be greater than the controlling torque, then the system, we call it underdamped. Actually, in ideal situation, we want them to be equal and opposite. And if it is exactly equal to the controlling torque, then we can say the system is critically damped. That is, it will be on a stable condition. But whenever the deflecting torque is less than the controlling torque, then the system, we call it overdamped, because the movement of the pointer will not give accurate result. It will not reach the point it's supposed to reach, because the controlling torque is higher than what? The deflecting torque. If we look at this diagram, you can see that we have a line here. This line that finally stabilizes at this horizontal is what we call a critically damped system. Any line that is below it, we call this one overdamped, and the one that will exceed the level, the horizontal line, and finally keeps on oscillating before it finally stabilizes, we call it the underdamped system, because it allows overshooting and it keeps on oscillating for some time. Now, what are the details that we're supposed to know when constructing any analog instrument that have these moving pointers? The first thing is, let us look at the moving system. The moving system should have the following properties. That is, the system that will be responsible for the movement of the pointer from 0 point to the point which corresponds to the signal we are measuring. The first one, it has to be light. That is, it shouldn't be heavy, because the lighter it is, the easier for the signal to deflect the pointer. The second one is the frictional force should be minimum, because you cannot have zero friction, so it should be minimized to the best we can. And this make the power requirement of the system to be very small, because if the something is light and the friction is small, then there will be ease of movement, therefore the power requirement should be small. And the moving system can be made using a light materials like aluminum. Aluminum, we know it is a metal, but it is not heavy, so it satisfies the requirement for the moving system of any analog instrument. And the frictional forces that we said should be minimum. It is possible for us to reduce them by using what we call a spindle mounted jewel bearings. The bearings that are responsible for the smooth movement, we can use this type, a spindle mounted. And they are also, it is very possible to reduce our friction by careful balancing the system to make sure that everything is in the right position. Now, the next thing is how do we talk about the controlling system, because we have seen that we have two types of three, of course, torques: the deflecting, the controlling, and the damping. So we have already talked about the moving system. It should be light, it should have less friction, and we have seen the method for selecting light materials, and of course for making the friction to be very small by using the spindle mounted bearings. Now, the controlling torque is provided by our spring or by gravity, as I've already said. So let us look at the spring version of the control. If you look at this diagram, here is a control spring, and also if you look at it, here is the same control spring. So we use what we call a hair spring. Usually it is made using phosphor and bronze as the materials that give us the hair spring. And the schematic diagrams are given here. This is my figure A on the left hand side, and this is figure B on my right hand side. As you can see here, we have our control spring, and here in the vertical position it is the same, our control spring. And as I said, it is the one that is producing equal and opposite torque to the deflecting torque, so that it can take it to a stable position. And even when you remove the system you are measuring, it will now bring to the 0 point. So the number of turns that are required for this spring, they should be fairly large, so that the deflection per unit length should be small. That is to improve the amount of the controlling torque, so that it will balance the signal we are trying to measure. Let us assume the length of the material used for making the spring is L in meters, and the cross-sectional area is rectangular. And let us assume the thickness is also T in meters, and the depth is B. Because we say rectangular, it must have length times breadth, or the depth in otherwise. Let's say the depth is B in meters also. And we assume E is the Young modulus of the material used for making the spring in Newton per meter square. So now, if we assume theta is the radiance deflection, that is the angular deflection whenever we put a signal that we want to measure. So the total controlling torque that the spring will provide is given by this: Tc equal to E B T cube all over 12L times theta. We define E, B, T, and L. All of them, the definitions are here. Now, so this controlling torque, if you look at it, it is directly proportional to the angle, provided all these other parameters, the E, the B, the T, and L, are constant. So the controlling torque is proportional to the angle of deflection of the pointer from the 0 point. Now, that is about the spring control. The second one, as I told you, we can use a gravity for controlling the providing the control torque. And in this, small weight is attached to the moving system. As we know, whenever you have a weight, it is being attracted to the ground due to the force of gravity. So that this weight will produce a restoring controlling torque. That is a force or a torque opposite to the deflecting torque whenever you apply your signal and create the deflection. And this is illustrated here if you look at this, this is like the tail end of the moving pointer, and we attach a weight here. It is here, and of course it is here. We have different positions depending on the point at which our pointer is moving. So the amount of this weight you attach to this end of the pointer is responsible for providing the controlling torque using what? The gravity. So the next thing is this controlling torque. If you are using weight, so T is equal to omega L sine theta, where theta is the angle of deflection, and this omega stands for the weight we attach to the moving part, and L is the distance from the axis of the rotation, that is from the point at which the weight is attached. If we go back to this diagram, it means the distance from where the something is attached to the point of rotation. Now the amount of gravity or the control torque provided by this gravity controlled instrument, it must be used in a vertical position, because if it is vertical, that is when the earth will be attracting it, but anything that is horizontal, it is not subjected to any gravitational attraction. So it has to be in the vertical position in order to make sure that the control may operate. As I told you, in the vertical position there is gravitational attraction. In the horizontal, it is like level to the earth, no acceleration due to gravity. So the next thing is, let us compare the spring and the gravity controls, because we have seen two of them. You can use a hairspring to produce a controlling torque, and you can use a weight attached to the moving part of the pointer. So let us compare the two. So the gravity control has the following advantages, and when it is compared to the hairspring, the first one, it is cheaper in terms of cost. The second one is it is independent of temperature, and the next one, it does not deteriorate with time. It is always there, because whenever you are using weight, it can be anything, so therefore it shouldn't be a special material, it will be cheap. And of course the temperature doesn't affect its weight, and of course it is not deteriorating, that is, it is not being damaged with time, it will stay longer than the hairspring. Now if we consider the instrument in which the deflecting torque is to be produced, and we assume this TD is proportional to the current, that is, let's say we are measuring the current, then we can now say TD is equal to KI, where K is a constant and I is the current we are measuring. So if the instrument is spring control, not the gravity, so the controlling torque, as we have seen, is CT, and the angle of deflection, we know it is equal to theta. So we can now say our TC, that is the controlling torque, is equal to KS theta, where KS is the spring constant and the theta is the angle of deflection. From our explanation, we said the controlling torque and the deflection torque are expected to be equal to one another, but acting in the opposite to each another. So we can now say KS, that is the spring constant, times theta is the controlling torque, is equal to KI, that is K is the constant for the gravity or the spring, and I is what? The current we are trying to measure. Now I can make theta the subject. Theta is equal to K over KS times I. So we can say the angle of deflection is directly proportional to the amount of current we are measuring, where K, we have seen it is a constant, and the KS is the constant of the what? The spring itself. Now if we are using a gravity controlled, on the other hand, we have seen previously that our TC, the control torque, is equal to kg sine theta, where kg is the constant depending on the weight we attach to the moving parts. And of course this weight has another effect with respect to the distance from the point of rotation, that is the point at which the pointer is rotating. And even in this case, our controlling torque must be equal to our deflecting torque, which is Ki. So I can now say kg sine theta is equal to Ki. So sine theta is equal to K over Ks times I. To get theta, I'll take the sine inverse of both sides, which means my theta is equal to sine inverse of K over Ks times I. This is the expression for my theta, that's the angle of deflection, with respect to the constant for the weight and the current we are measuring. Now, we have seen apart from the controlling and the deflecting torque, we have damping torque. And let us see, there are so many three systems of damping generally that we are using. And these are, sometimes you can damp it using air friction, you can use a fluid friction, and you can use eddy current for the damping, as I've already mentioned previously. Let us look at the air friction. For instance, whenever you are using an aluminium as your moving parts, and it is used also as a piston, and the piston, as you can see from this diagram, is like a tube into which the end of our piston, our moving part will enter. And we assume that this aluminium is attached to our moving system. When it is moving, the air inside the chamber, inside the piston, will be closed at one end while it is open at the other end. And you know, whenever, even if you are moving, there is what we call an air friction, even if you are moving with a car or anything. So the movement of this handle that is going into the aluminum piston and coming out, it will be experiencing opposition because the other end of the piston is what? Closed. So the cross section of the chamber, it can be circular and we can make it rectangular depending on what we need. So the clearance, that's the distance between the body of that piston and that arm which is going in and out. The on both sides, we should make it to be very small and it should be uniform. That is on the right hand side, below, up, and the left hand side, the clearance must be equal, because if there is variation, the friction that the air will be producing will change the damping effect. That is for the air damping. The second one is a fluid, and if we say fluid, of course we are talking of liquids. And whenever you want to use this system, as you can see from this diagram, I have my container, and inside it I have an oil, which is our fluid for that. And here I have my moving part, which supports a part that is going down into the liquid and going up. If you get a light vein and you attach it to your spindle of the moving part of the system, that is the system that is attached to your pointer, and you put it inside a pot that has the oil. Whenever you are trying to push it down, you have to displace the oil, and in trying to do that, you are experiencing an opposition, and that opposition is what is responsible for producing this damping. We said fluid friction. We mean the resistance as the end moves inside and when it is coming off from the liquid. Now, if you look at this, we have figure A, and of course you can use figure B. Here we are like using platen, but here we have four arms which are located opposite to one another. So as this end is moving down, it will be experiencing what we call the upthrust, and it is what? The friction created by the oil, and that is responsible for creating the damping effect. The last one we mentioned is what? The eddy current damping. And as I told you, if you can remember your physics in secondary school, we know what is an eddy current. And to do this, it is achieved using these two diagrams. We use a sheet of conducting material, that is metal, and we move this material in a magnetic field. Definitely the eddy current will be set off. If you can remember your transformers, the metals, the core on which we wind our wires, whenever there is change in the magnetic field, an EMF is produced, and that EMF will create heating current that is like a waste, and of course that is the eddy current. So this amount of current is directly proportional to the velocity of movement of this sheet in the magnetic field. So if the magnetic field is constant, it doesn't change, so the damping force will now be proportional to the velocity of the moving system. So in this way, we create a current which is acting in opposite. It will be opposing the movement of the pointer when you attach it to any, or you connect it to any electrical source you want to measure. So it will create an opposite force, which is our controlling art. Now let us assume the velocity is linear. V is equal to omega r, as we know, where omega is the angular velocity, where r is the diameter over 2. Since it is a linear velocity, we can now say it is radius times what? The angular velocity, as I've explained here. So the amount of EMF generated, EC, is given by 2 BLV, where L is the length of the, is the length of the material, and V is the velocity, and this B is the magnetic field, magnetic flux. Now I can say 2 V L. Instead of putting this V, I'll put d over 2, which is radius times what? Omega, as we have defined the velocity here. Now the 2 can cancel 2, and my EC is equal to BL d W, where W is an omega, is our angular velocity. Now the resistance of the path through which that current will flow, RC, is given by this formula, where rho is the resistivity, D is the dimension, and L is also dimension, and our B is the depth, and the T is the thickness of the material. Now the eddy current that will be produced from this is equal to the voltage over resistance, that is IC is equal to EC over RC. So if you say this guy over this, you end up getting this. This is algebraic simplification, you can do it. So if this is the current, the damping force is given by B IC times L. So if you say this is your IC and this is your B, look at it, it is already exists in the formula of IC, it should be square, and this is my I, which is the amount of current. And finally, the damping torque, we know the torque is equal to force times what? D, which is the distance of the movement. So I'll multiply this force times D, I will have this. So finally, my damping constant KD is equal to the torque all over omega. And if you divide this expression, which is our TD, by omega, you come up with this formula, which is the damping constant using the eddy current damping. So ladies and gentlemen, this is the end of our lecture number 4. I advise you to watch this video over and over again. God willing, it will be very easy for you to understand everything. Thank you. Till we meet in our next lecture. Thank you.